Okay, here we are with our logic that we edited, created all the new tags, aliased it to the former base tags, or the former module defined tags that are now the base tags. And we've downloaded, we're in the remote run mode. And we ask you that the stop switches should be on and the start switches off. So if you look up here, the stop is on in both of these instances, and the start switches are off. Now in the future, you will use a normally closed switch for the stop switches. Fail open is fail safe. Now because we're using toggle switches, we can toggle those switches on, the ones we're using for the stop inputs, and just consider that a normally closed button, because right now it's closed. It's at rest in the closed position. Keep it in mind that it's a toggle switch, so it has two at rest positions, open and closed. But in my case, with the digital field device simulator that I do have one normally closed push button that I could have integrated into this. I'm not going to, because this requires two stop buttons, and I didn't want to confuse the learning process by applying two different methods of doing the same thing. So we're just going to stick to toggle switches for right now. What is the state of each input device used? Local, one-eye data 0. What state is it in right now? Well, local one-eye data 0 is off. Local one-eye data 1, is it on or off? Well, if you look, you see that local one-eye data 1 is on. That's the stop. Local one-eye data 2, is it on or off? Well, you can see it's on there. If this is true if on and it's highlighted, then it's on. This is true if off. It's highlighted, therefore it's off. You know, after a while, if you look at the code enough, especially online in the run mode, it'll all start to make sense at you. I mean, I instantly look at this and see that that's not off because it's not true. This is a true if off instruction. It's not true, therefore it's not off. It's on, as you can see up here. It's on. If a true if on instruction is highlighted, then that bit is on. If the true if off instruction is highlighted, then that bit is off. Toggle both start motor 1 and start motor 2 on, then off. Start motor 1 would be 0, and we go back off, but you see it's still running. And then start motor 2 is 3, we'll go on and back off. So both motors are running, but the start buttons are now off again. Motor 1 is on because the OTL does not have a false execution. Motor 2 is held in the energized state by its own bit, local 1 O data 2, aliased to _2M, which logically bypasses the start motor 2 button. If this were a relay circuit, the top two would be the circuit diagram for a latching relay. Remember, a latching relay has two coils. One coil closes the normally open and opens the normally closed. In other words, that when you energize the coil, the contacts change position, but they mechanically latch into that position. So you turn it back off, they stay that way until you make this circuit have a complete path for conductance and energize this coil. This coil then pulls the latch away from the contacts and lets them go back to the normal position. Electrically, you have two coils. Here you only have one, but this, if this were an electrical circuit, this would be a stop push button, a start push button. Now that would be normally closed if this was an actual push button, electrical circuit. So as long as you're not pushing a normally closed, it's closed and you have continuity. When you push this button, the normally open, closed, energize this coil. This contact right here is part of that coil. So if this were a relay, this would be and you call this relay CR2, contact relay 2. This would be CR2-1. It would be a contact that's mechanically connected to this coil. You push the start button, it energizes this coil, closes this contact. So now you have current flowing through both of these contacts to this relay coil. When you let go of the push button, it continues to flow through its own contact. It is self-sealing. It is sealing logic. Both of what you see in front of you, these two methods, and aside from the fact when you leave the run mode and come back, you lose the bottom rung. Aside from that, these two work 100% identical. Personally, I prefer this logic down here because it's all one rung. What starts it and stops it and keeps it on is all in one rung. These two rungs could get separated. In other words, if you had 300 rungs in your program, it is possible that one of these could get separated from the other, and then when you're troubleshooting, you see that it's on and you want to find the logic to turn it off. Well, you have to do a search. You have to do a cross-reference. Whereas this one, this rung, all the logic is right there. You can see what turns it on and what turns it off and what keeps it running. So I personally prefer this. Plus, if I'm actually starting or energizing field devices that can cause motion, like solenoid valves, motors, etc., I want those outputs to drop out if they go into the program mode. I don't want them to turn it back to the run mode and then all of a sudden have some unexpected motion and something gets damaged, especially if it damages the operator. And once again, we demonstrated what I pointed out in an earlier video, even though we weren't this far in the lab book yet. I had you go to the program mode and then watch 2M, watch the last rung, and then go back to the run mode. See, you lost the on state of 2M but not of 1M. And that's because on the very first program scan, OTEs are treated differently than OTLs and OTUs. Were any of the output devices affected by cycling the mode? Yes. Which outputs were affected? 2M, local 10, data 2. Why? Because when you go to the program mode and back on the very first program scan, OTEs are treated in such a way that they are treated as off for the first scan. If you came through and it was treated as off, then this whole thing would be false and it would tell that to turn off. So the very first program scan, it turned it off. Well, you didn't see that because it's 20 microseconds. Return the state of the logic to what it was before you cycled the mode. In other words, start 2M and then off. So we use 3 to start 2. Cycle the power to your controller. And this is a little bit more involved. So we're going to cycle the power to the controller. And of course you see we're losing communications. You see the little swirly here. So right now RS Links is, yelling out there, hey, what's going on out there? Well, eventually it's not going to, since it doesn't hear an answer back, it's just going to time out. Can't communicate with RS Links, RS Logix 5000 is taken offline. Say OK. And we'll go back to online. Okay, we're back online. Now we didn't cycle the mode, but in a way we did. Notice what happened. By removing power from the controller and reapplying it, we lost this on state. So there is no difference between cycling the mode or cycling the power. But notice that we did not lose the state of local 10 data 0. It stayed 1. Were any of the output devices affected by this power cycle? Yes. Which outputs were affected? Local 10 data 2. Because it's being instructed or executed against an OTE instruction, output energize. If we look at the description of operation of these instructions, it's in the manual. I'll read it, but you should look at it. You should go to help, instruction help, and I may have showed you that in the manual. Maybe I did, maybe I didn't. And we want to go to bit instructions. I always have to search down through here. Alarm filter, bit instructions right there. And we go to OTE. And if you look down here, ladder diagram, condition, pre-scan, the data bit is cleared. The run condition out is set to false. Okay, that's how it does it. Run condition in is false, the data bit is cleared, the run condition out is set to false. The pre-scan is going to set it to false anyway. If the run condition in is true, the data bit is set. But remember, this run was false because when we lost this bit, in other words, it turned this bit off, which then made this instruction false, and because this wasn't true, the whole run was false, and it sets that off. Okay, so this is the state here for the OTE. If we back up and go to the OTL, come down here and look, pre-scan, the data bit is not modified. The run condition out is set to false. Now right there, that tells the whole story. And I don't know which came first, the cart or the horse, because this instruction, the OTL, has no false execution. Then setting the run condition out to false is not going to affect that bit. So whether you want to say it's not modified or the run condition out is set to false, which won't modify it because there's no false execution. So I think we beat that horse enough. The key phrase here is not modified in both cases. OTE and OTL, the run condition out is set to false before the first scan. The OTE has a false execution, but the OTL does not. Okay, save your project as, I guess, aliased, so we'll just save it. You don't have to upload the tags, and that will conclude this section of the manual.